All right, so welcome back to our class video. Okay, so in this class, I'll be taking you guys gravitation. Okay, I'll be taking you guys gravitation, and this class video is divided into 6 categories. Okay, the very first category talk about the definition of gravitation. The next one, move to the laws of gravitation. Then move to weight and altitude, satellite motion, orbital period and parking orbit. Then do questions and answer. Okay. So now let's start with the very first part, which is the definition of gravitation. Which is the definition of gravitation. Now, what is gravitation? Okay. What is gravitation? Now, gravitation is the force of attraction. Please take note, okay? It's the force of attraction between a massive object. Okay? It's the force of attraction between a massive object and a less massive object. Okay? So, gravitation is the force of attraction between a massive object and a less massive object. For example, let's say the sun and what? The sun and what? The moon. I mean the sun and the earth rather. Okay. So that force of attraction between a massive object and a less massive object is known as gravitation. Okay. You can also define it as gravitation is can also define it as gravitation is the force exerted by a massive object on a less massive object. Okay, yes. So that is the definition of gravitation: force of attraction between a massive object and a less massive object, or the force exerted by a massive object on a less massive object. Now, if you look at this, the sun is more massive than what? Than the earth. Okay, yeah. So that is just it. It can also be between the earth and what? Between the earth and what? The moon. So that is just it. Okay. Now, before I continue, please take note of this part. This place here is very important. Please take note of this part. Okay. Now, this first part, this is the mass. The mass of the sun. Please take note. Is approximately. Okay. Now, the mass of the sun is approximately. Please, it's very important. 1.9 times 10 raised by what? 30 kg. Okay, yes. This is the mass of the sun. Okay, theoretically, this is the mass of the sun. Or you can approximate it as what? 2 times 10 raised by what? 30 kg. Okay, so this is the mass of the sun. 2 times 10 raised by 30 kg. Okay, yes. Please take note. Then the next one is the mass of the earth. The mass of the earth is approximately it is 5.97 times 10 raised by what? 24 kg. Or when you approximate, it can be what? 6 times 10 raised by what? 24 kg. Okay, please put this. It's very important. Take note of them. Okay, this is what the mass of the sun. This is the mass of what? This is the mass of the earth. Okay, it can be 5.97 times 10 raised by 24 kg or 6 times 10 raised by what? 24 kg. Yes. The mass of the sun can be 1.9 times 10 raised by 30 or 2 times 10 raised by 30 is the same thing. Then the last part, this is the radius of the earth. Please take note. The radius of the earth, because we'll make use of these things later. Later on, we are going to make use of these things, okay? The radius of the earth is what? Is 6.4 times 10 raised by what? 6 meter. Okay? This is the radius of the earth in what? In meters. 6.4 times 10 power 6 meter. Okay, so please, this part is very, very important. Okay, yeah, take notes. Now let's move to laws of gravitation. Okay, now there are different laws of gravitation. We have Kepler's law. We also have Newton's law. Okay, now under Kepler's law, there are 3 Kepler's law. The first law, the second law, and the third law. Okay, but in this video, I will just the most important part you need to take note of under this law is the third law. Okay, so I will not bother. I will not state the first and second law. I will all go straight to the third law. Okay, now we have Kepler's law. We also have Newton's laws of gravitation. Now, Kepler's law, there are 3. The first law, the second law, and the third law. Okay, now the third law, which is very important. Because there are a lot of calculation questions from this aspect. Okay, now the third law of Kepler's third law states that, please take note, state that the ratio, it state that, okay, yeah, it state that the ratio of the period, I'm coming. Now, it said that the ratio of the square, remember T, this T is time, or you can say period, okay? So Kepler's third law, it states that the ratio, this ratio, now the ratio of the square, the ratio of the square of the period of planets. I don't even understand. The ratio of the square, the ratio of the square of the period of planets is equal, or is actually is proportional to the ratio. Okay, I'm coming. It's proportional to the ratio of their proportional to the ratio of their distance, of the cube, rather, of the cube is proportional to the ratio of the cube of their distance from the sun. Okay, that is just it. Okay, so this is Kepler's third law, which states that the ratio of the square of the period is equal to the ratio of the cube of their distance. You can call it distance or radius, okay, of their distance from the sun. Okay, so this is Kepler's third law. Okay, please take note of this formula. Okay, this is the very first formula. Please, if I tell you to take note of something, please take note, because you're going to use it to solve later on. Okay, so this is Kepler's what? This is Kepler's third law. Okay, this is Kepler's third law. Okay, this arrow, we can see turn it to be what? D. It's the same thing. Okay, we stand for distance. Okay, let me just use D. Okay, the same thing. Okay, so this period T1 is for the first planet, T2 is for the second planet. This distance is for the first planet, then this distance for the second planet. Okay, so this is Kepler's third law. Please take note of this. Okay, now let's continue. Let's go to Newton's laws. Okay, remember laws of gravitation. We have Kepler's law, we have Newton's law. Okay, Kepler's law, we have the first law, the second law, and the third law. This is the third law. Please take note of this formula. We are going to use them now. Newton's law. Okay, Newton's laws of gravitation. Universal Newton's laws of gravitation. Now, Newton's law of gravitation state that. I'm coming. Newton's laws of gravitation state that. Okay, state that the force of attraction between two masses, or we can say the force of attraction between two objects, is directly proportional to the product of their masses. Okay, said that the force of attraction between two objects is directly what? This sign is directly proportional. Okay, is directly proportional to the product of their what? To the product of their masses. Okay, is directly proportional. He said that the force of attraction between two objects or between two masses is the force of attraction. The force of attraction between two objects is directly proportional to the product of their masses and inversely proportional to the square of their distance. Okay, to the square of their distance. Okay, yes. Now, if you remove this proportional sign and place a constant here, it will now be what? G. Okay, M1 M2 all over our own square. Okay, so this is what? This is Newton's universal law of gravitation. Okay, we state that the force of attraction between two objects or between two masses is directly proportional to the product of their masses and inversely proportional to the square of what? Of their distance. Now, G, which is known as gravitational constant. No, please take note. G is what? G is what? Gravitational what? Gravitational constant. Okay, gravitational constant. Okay, yes. Please take notes. Okay. Now, gravitational constant, the value for G is what? G is equals to what? G is equals to what? 6.67 times 10 raised by what? Minus 11. Okay, so this is the constant. So this is the value for G. Okay. The first thing I told you guys to take note of. I told you guys to take note of this place, right? Yes. Now, the second one I told you guys to take note of is Kepler's third law. Then the next one, this is universal law of gravitation. Okay, yes, where G is what 6.67 times 10 to the minus 11. Okay, yes. Now we are done with the laws of gravitation. Now let's move to weight and attitude. Okay, so I'm coming. Let me clean. Okay, all right. So yes. Now let's continue with let me clean this part. I'm coming. Okay, don't forget that I'm coming. Don't forget, please take note. Don't forget that Kepler state law is the square of their period. Okay, the ratio of the square of their period that proportional to the cube of their distance from the sun, right? The ratio of their cube of their distance from the sun. Okay, yes. Okay, this is Kepler's third law. You can put D, you can put R. Okay, then this is Newton laws of gravitation, right? Yes. Okay, where G is what is equals to 6.67 times 10 to the power minus 11, right? Yes. Now let's move to weight and attitude. Okay, now where is weight? Okay, so the weight of an object is the gravitational force of attraction. If that's what is weight, what do you understand by weight? Weight is just the force of attraction between the earth and an object. Okay, yes, the gravitational force of attraction between the earth. Please take note. The force of what? Force of attraction between the earth and what? And an object. Okay, yes, that's known as what? Weight, right? Yes. Remember, weight is equals to what? Now remember, we all know that weight is W, right? Yes. And is a force. Weight is a force, right? So we in place of W I put F, right? Weight is a force. So this is weight. Okay, so the weight of an object is what? Is the force of attraction. Is the force of attraction between the earth and that object. I don't even understand. So it is what? Is the force of attraction between the earth and what? Between the earth. Force of attraction between the earth and what? And that object. Okay, and that what object. That is weight of that is weight. Okay, yes. Now we all know that weight is equals to what? Mg, right? Yes. And weight is what? Is the force of attraction between the earth and what? And that object, right? So in the place of this F, I will put this one here. Okay? I'll put this. Okay? Remember, weight is what? Force of attraction between what? Between the earth and what? And the object, right? Remember, this is arrow square, then is equals to what? Mg. Okay? Weight is what? This is weight. Weight is what? Force of attraction between the earth and the object, right? Yeah, where this arrow square, this is the distance between the object and what? And the earth. I don't understand, okay? So let's derive. Okay, this is all about this topic. It's all about derivation and some theoretical aspects, you are going to take note of a lot of formula. Okay. Okay, so this is the mass of the object, this is the mass of the object. So this one will cancel out, right? Yes. We'll be left with what? G N E. N is stand for the mass of the earth, right? Divided by what? Arrow square is equals to G, right? Yes. Now if we cross multiply, we'll be left with what? Okay, now before I continue. Now this distance, this distance is what? Is the radius of the earth. I don't even understand. Is the radius of the earth. Okay. Now this distance is what? I'm coming. Okay, this distance is what? Is radius of the earth. Okay. Yes, radius of the earth. So this one will cancel. They will cancel each other. We'll be left with what? G is equals to what? G is equals to GME all over what? Arrow E square. Okay, please take note of this formula. Okay. G is what? Is gravitational constants times the mass of the earth divided by what? The radius of the earth. You see this letter E here. This E shows that this is earth. E stands for earth. E stands for earth. So mass of the earth, radius of the earth. Okay. So this is what? This is formula for G. Okay. Okay. This can also be gravitational intensity. Okay. So yes. Now, please take note. If we cross multiply, right? Let me clean this part. Okay, we have already noted this. Now, if we cross multiply, remember G is equals to what? gravitational constant times mass of the Earth divided by what? The radius of the Earth, right? Yes. Okay, now if we cross multiply, we'll arrive at what? G arrow E square is equals to what? Capital letter G, then M E. Now, please take note of this. It's also important, okay? All right, so we are going to make use of them later. Okay, so I'm coming. I'm going to make use of them later. Okay, take note of this, take note of this, take note of this. Then let's take these two are the same, right? So let's take note of that one. G arrow E square is equals to what? G N E. Okay, all right, so it's very important. All right, so let's continue. Now let's continue with, I've talked about weight. Now let's continue with what? With altitude. Altitude, okay? Altitude. Okay, altitude. Now what is altitude? Altitude just means height, okay? Yes. When an object, let me use the satellite for an example. Let's say this is the Earth, and let's say this is the satellite, right? Now, when an object is placed above at a particular distance above the Earth's surface, now this is the Earth's surface, right? Yes, and this is the object. Now, when an object is placed at a particular distance above the Earth's surface, now that distance to the Earth's surface is known as what? Is known as altitude. Okay? Yes, it's known as altitude. When an object is placed at a distance above the Earth's surface, now this distance between the object and the Earth's surface is known as what? Is known as altitude. Okay? Yes. Now, that's known as altitude, right? Yes. Now, remember, this radius of the Earth, right? Radius of the Earth. Radius of the Earth, right? Arrow E. This is radius of the Earth. Now, this is altitude. Altitude is that distance above the Earth's surface. Okay, distance between the Earth's surface and what? And okay, we can say this distance between the Earth's surface and what? And that and the object. Okay, that's known as altitude. It's known as altitude. Okay, yes. Okay, yes. Now, then what is the distance? Then okay, this is altitude, right? Yeah, this is the radius of the Earth. That is from the center of the Earth. Radius of the Earth is just the distance from the center of the Earth to its surface, right? This is known as what? Radius of the Earth. Now, when an object is placed at a particular height above the Earth's surface, this height is known as what? Is known as what? Is known as altitude, right? Yes. Now, the total distance between the center of the Earth and that object is known as what? It is the total distance. We call it arrow. Okay, so arrow will be what? Is because to what? Because to the radius. Now, this one is known as what? The total distance. Okay, the total distance from between the center of the Earth. Okay, I'm coming. Okay, let me just clean it. All right, I'm coming. So arrow will be what? Arrow will be what? The total distance between the center of the Earth and what? And that object. Okay. Yes. What about the radius of the Earth? From the center of the Earth to the surface of the Earth, that is the radius of the Earth. Then altitude is what? Is distance. Above the Earth's surface. Okay. Distance between the Earth's surface and the objects. Okay. That is placed above the Earth's surface. Okay. So now the total distance between this object and the center of the Earth is arrow. Okay. Is equals to what? The radius of the Earth, then plus the altitude, okay, the height at which the object is placed above this Earth's surface. Okay, so that is just it. Okay, let me do it again. Yeah, let's say this is the Earth, this is the object. Okay, so the distance between the Earth's surface and the object is known as what? Is known as altitude. Then this is the radius of the Earth. Okay, this is the radius of the Earth. Now, the total distance between the radius of between the center of the Earth and the object is known as arrow. And arrow is what? Is both the radius of the Earth plus what? Plus altitude. Right? So please take note of this. And remember, don't forget about the radius of the Earth. The radius of the Earth is what? 6.4 times 10 raised to the power 6 meter, right? Yes. Okay, so now let's continue. Okay, we have talked about weight and altitude. Okay, yes. So This I told you guys taking note of this. This is number one. Taking note of this. Then our next one was number two. Taking note of this. Number three. Taking note of this. Number four. Yes. Then number five. Okay. Yes. Taking note of this. All right. So let's continue. Okay, so because it's very very important. Okay, note that gm, that is gravitational constant times the mass of the earth, is equals to what? G times the radius of the times the square of the radius of the earth. Okay, yes, very very important. Let's move to this part. um Satellite motion. Okay, satellite motion. Okay, let me clean it. I'm coming. Satellite motion. Okay, satellite motion. Okay. Now, what is a satellite? Satellite motion. Now, what is this? Satellite motion has to do with what? Has to do with the motion of a satellite, right? Now, what is a satellite? Satellites are objects. Yeah, these are objects that revolve. That revolve what? Are objects that revolve around the planet. Okay. Specifically, let's use Earth now, for example. Satellites are objects that what revolve around the Earth. Yes, they can be natural. They can also be what? Artificial. Okay, we have natural satellites. Example of a natural satellite is what? Is the moon. Okay, the moon is Earth's natural satellite. Okay, a satellite is what? Is a body that revolves what? Using the Earth as an example, satellite is a body that revolves what? Around the Earth. Okay, a body that revolves around the Earth. Yes, they can be natural. They can also be artificial. We have natural satellites. Example of natural satellite is the moon. Then artificial satellites, for example, those communication satellites, okay, yes, those ones are man-made, okay, those ones they are examples of artificial satellites, okay. The moon is Earth natural satellite, okay. So now let's continue. Now satellites, I told you guys that satellites, these are objects that or bodies that revolve what? Revolve around a planet, that revolve around the Earth, blah blah. Now, a bodies that revolve around. You can also call it that. You can also say something like these are bodies that revolve around a massive body. Okay, any definition. Okay, so now let's continue. Under satellite motion. Now, I'm coming. So satellites are bodies that revolve around the Earth, right? Yes. Now there is a force of attraction. Now, what enables this object to revolve around the Earth? Is a result of what? Is as a result of the gravitational force of attraction between what? Between the Earth and what? And that object and the satellite rather. Okay. So um this is what makes this is what keeps the object that to keep on revolving what around the Earth. I don't know if you understand. Okay. Now there's usually what? A force of attraction between the Earth and the satellite, or rather, there's a force of attraction between the Earth. Yeah, there's a gravitational force of attraction between the Earth and the object. Okay. Yes. Now it is this gravitational force that provide. Remember, satellite they do what? What do satellite do? Satellite they do what? They usually revolve. They revolve around what? They revolve around the Earth, right? Yes, they revolve around the Earth. Now, don't forget that there's a gravitational force between what? There's a gravitational force between the Earth and what? And the satellite. And this force is what prevents this object from. Okay, yeah, it's one that usually keep gravitational force is one that that usually keeps satellite to be around this orbit. I don't know if you understand. Okay, yes. Now, it is the gravitational force that provide the centripetal force. Remember, don't forget, satellite they are what? They are moving in circular path, right? Around the Earth. Yes. And that type of motion is known as that is a circular motion, right? Yes. And what keeps a body moving in circular path is what? Is centripetal force. I don't even understand. So it is the gravitational force between the Earth and the satellites. Please take note. It is the gravitational force between the Earth and the satellite that provide or that produce the centripetal force that keeps this body to move what? In circular path. What is centripetal force? Centripetal force is what? Is an inward force that keeps a body to what? To keep on rotating what? In a circular path, right? Yes. Now, in the aspect of satellite motion, what keeps a satellite to keep on moving circular path is the centripetal force that is provided by what? By the gravitational force between the Earth and the satellite. Okay. Yes. Now let's do some derivation. Okay. So this centripetal force, right? Centripetal force. Okay. Centripetal force. Now what provides the centripetal force? This is the Earth, right? This is the satellite. Satellite is moving around the Earth, right? Yeah, moving in circular paths around the Earth. Now, what produce this centripetal force, right? Now, what produces centripetal force? It's what? It is what? The gravitational force. I told you guys, yes. It is the gravitational force between the Earth and satellite that produces the centripetal force that make the object to keep on revolving around the Earth, right? Yes. So let's say that let me just use it like this. I'll say, okay, Fg equals to what? Fc. Okay, yes. So it is gravitational force that produces the centripetal force that enable the satellites to keep on revolving around the Earth. Yes, that enable the moon or any computation satellite to keep on revolving around the Earth. So it is gravitational force between this Earth and that satellite. It is that force that provides centripetal force that make the object keep on revolving around the Earth. Okay. Now, where's the formula for? I'm teaching you guys how to derive um, the equations. Okay. Now the Fg is equals to Fc. Okay. Yes. Now apart from that one, okay, this is the Earth and this is the satellite. Now satellite, they're usually what? They're usually revolving around the Earth, right? They're usually revolving around the Earth at a constant speed. Okay. Now, please let me tell you guys something. Okay. Now, satellite they either orbit in what? In they either orbit in a they either move in a circular orbit. Okay, it's very important. Satellites they either move what? In a circular orbit, or some move in what? In an I'm coming eclipse. I don't know how to spell it. Ecliptar. It's ecliptar. Okay, I think I spell it wrong. Okay, ecliptar orbit. Okay, yes. Okay, ecliptar orbit, circular orbit. Okay, I don't think this spelling is correct too, but you can go research it. Now let's continue. Now satellites they usually move. Some satellites usually move in circular orbit. This is an example of a circular orbit. Okay, this is an example of a circular orbit. Okay, yes. Now some satellites, most satellites usually move in circular orbit with a constant speed. Okay, most satellites usually move in a circular orbit with a constant speed or a constant velocity. That speed with which a satellite is moving is that speed which is that constant speed in which a satellite is moving is known as what? Is known as orbital. It's known as orbital velocity. Okay, you can call it orbital velocity or what? Or orbital speed. Okay, yes. That constant speed, I will come back to the ecliptic orbit, okay? Now that constant speed in which a satellite used to orbit in a circular, in which a satellite used to move in a circular orbit, that speed is known as what? Is known as orbital velocity or what? Or orbital speed. Okay? Yes. Now let's derive this velocity. How are we going to get the formula for this velocity? We are going to use what? This formula, okay? Remember, the satellite is usually moving around the Earth, right? Yes. And that type of motion is a circular motion. Yes, that circular motion is provided by what? Provided by centripetal force. Centripetal force is what gives out the satellite to move in circular path. And that force is provided by what? The gravitational force between the Earth and that object, right? Now, one formula for gravitational force, this formula for gravitational force, right? Which is um, G M. Okay, I'll put M E then M all over what? Arrow square. Then equals to what? So it's formula for centripetal force. Actually, guys, formula for centripetal force is what? Mass times velocity, the square of velocity times what? The radius. Okay. Yes. Now, I'm coming. I'm coming. Okay, so let's say this is the Earth now, and this is the satellite, and satellite is moving around. Okay, so I'm coming. Okay, so this mass is the mass of the Earth. Then this other mass is what? Is the mass of what? Is the mass of the satellite, right? We are going to we want to derive what? Orbital velocity. So we cancel this, right? We'll be left with what? GME all over rho square. Okay, yes, equals to v square over rho, right? Yes, because of v square over rho. Okay, now let's continue. I'm coming, let me clean this part. Now, okay, if we cross multiply, we'll be left with what? GME rho equals to v square rho square, right? Yes. Let's divide both sides, okay, by rho square. Divide both by rho square, we left with what? V square is equals to what? GNE rho then divided by what? Rho square, right? Yes. Now this one will cancel this. We'll be left with what? One rho, right? So v square is equals to what? GNE divided by what? Rho. Okay. So, oh, we are not done yet. Okay. So now, if we want to make v stand alone, we take the square root of both sides. This square will cancel this square root. We left with v is equals to what? The square root of GNE all over what? Rho. So this is the formula for what? For orbital velocity. Okay? Orbital velocity. Alright? So this is formula for what? Orbital. This formula for orbital velocity. So this is the formula for orbital velocity or what? Orbital speed, right? Yes. Now, there's something I want to tell you guys. Now, if you look at it, v is what? V is equals to what? The square root of gravitational constant times what? The mass of the Earth all over what? Rho, right? Yes. Now this arrow. Remember, okay, I'm coming. Remember, this is the Earth, and this is what? This is the object that is revolving around the Earth, right? Now this arrow is what? Is this? I don't even understand. Okay, because why? Okay, I'm coming. Arrow is equals to what? From the radius of equals to radius of the Earth plus what? Plus altitude, right? Yes. So in the place of arrow, I will put what? I will put what? I will put in place of arrow, I put what? Arrow e plus what? Arrow e plus altitude, right? Yes. So this is the formula for what? This is the formula for orbital velocity. Okay. Orbital velocity is equals to what? The square root of the gravitational constant times the mass of the Earth divided by the radius of the Earth plus what? The altitude in which the satellite is placed. I don't know if you understand. Okay. Yes. So this is orbital velocity. Please take note of this formula. Now, there's still one thing I told you guys. Now, if you look at it, this is gravitational constant multiplying what? The mass of the Earth, right? Yes. Now, if you come to this part, you find out that gravitational constant multiplying mass of the Earth is equals to what? GRO associated to gravity multiplying what? The square of the radius of the Earth, right? So in the place of GME, I can put what? GRE square. Okay, so in this place, I can put what? GRE square because well, the equation, right? Yes. So B will now be what? Equals to what? The square root of what? In place of GME, I'll put what? GRO square, right? So GRO each square, then divided by what? Arrow E plus what? Plus altitude. Okay. So this can either be this formula can either be the formula for what? For orbital velocity or this one. You can use any of them. You still arrive at the same answer. Let me understand. Now there are any question. I will not give you this one. You can use this one very fast. This one, you know, G is 9.8, right? Or you can use 10. You know the radius of the Earth. Radius of the Earth is what? 6.4 times 10 raised power times 10 raised power 6, right? Divided by the radius of the Earth again, then plus the altitude. In the question, it will give you the altitude of the satellite. Take the square root of everything, you get your orbital velocity. Or if you want to use this other one, the constant for G is what? 6.67 times 10 raised to power minus 11, right? Times the mass of the Earth. Mass of the Earth is what? Is 5.97, or you can also say 6 times 10 raised to power what? 24. Okay, so if you use any of this formula, you get what? Orbital velocity. Okay, yeah, so this is formula for what? Orbital velocity. Okay, so take note of these two formula. Now there's still another one. Okay, I'm coming. Okay, there's still another one. Okay, but this is orbital period. Okay, so there's still another one. Now, when an object, please, this scenario, please, is very important. Now, this scenario is when what? Is when the satellite And let's say this is the Earth. Okay. Now this scenario is when the satellite this is at an altitude above the Earth. I don't understand. So this formula is you can use this formula to calculate for what? For orbital velocity. When the satellite is what? Is at an altitude above what? Above the Earth. I don't understand. So that is what you see in this formula, you see a share, you see a share. Because this formula is used to calculate for orbital velocity when the satellite is what? Is at a very far distance away from the what? At a very far distance. Let's say this is the Earth. When the satellite is at a very far distance away from what? From the Earth. I don't even understand. But if that's to calculate the orbital velocity of this satellite, you can either use this or use this, okay? Yes. What of when the satellite is placed at the surface of the Earth or close to the surface of the Earth? Let's say this is the Earth, for example. Now the satellite is somewhere here. Now if that's you, now when the satellite is at the surface of the Earth, and for example, when it's at the surface of the Earth, the distance between the Earth and the satellite will be what? Will be the radius of the Earth. Remember, so please take note of this formula, okay? I can claim it now. Yeah, please take note of this two formula, okay? So now this previous formula I told you guys is when the satellite is far away from the Earth, right? Now, but this one now when the satellite is closer to the Earth's surface, right? When the satellite is closer to the Earth's surface, the distance between them is approximately the radius of the Earth. I don't even understand. Now, let's say this is the Earth, and this is radius of the Earth, right? Yeah, this is radius of the Earth. Then let's say this is satellite here. So the distance between the Earth and the center of the Earth and the satellite will be what? Will be the radius of the Earth. I don't understand. Okay. So yes, distance between them is what? Is radius of the Earth, right? Yes. That is when the satellite is at the surface of the Earth. Okay. When the satellite is what? It's at the surface of the Earth or close to the surface of the Earth. The distance between the satellite and the Earth is just what? Is approximately the radius of the Earth, right? From here to here, that's the radius of the Earth, right? Yes. Now, when a satellite is placed at at the surface of the Earth, the formula you are going to use to calculate for the orbital velocity is different when the satellite is far away from the Earth. I don't know if you understand. When the satellite is far away from the Earth, the formula we use to calculate for the orbital velocity is different from when the satellite is close or is at the surface of the Earth. Okay. Now, which formula are we going to use to calculate for what? The orbital velocity when the satellite is close to the Earth's surface or when the satellite is at the Earth's surface. So it's very easy. Remember, it is the gravitational force that provided with the centripetal force, right? That enable the satellite to revolve around the Earth, right? Yes. When formula for gravitational constant force is what? Gm. Okay, we'll take this one as the mass of the Earth, then this is mass of the satellite divided by what? The distance between them, right? The square of distance between them is equal to what? Mv square. This is the centripetal force. Mv square over what? Over r, right? Yes. This mass, we cancel this mass, right? Yes. Now, this distance is what? Is the distance between what? The Earth and what? And the satellite, right? Yes. Same with this distance between the Earth and the satellite, right? Yes. So this distance is what? Is the radius of the Earth, right? I told you guys that when the satellite is at the Earth's surface, the distance between the center of the Earth and the satellite is the radius of the Earth, right? Yes. So when we cancel this one, we cancel this, we'll be left with what? One arrow, right? We'll be left with one arrow, right? So now if we continue, GME divided by arrow E because to what? Because to V square, right? Yes. Okay, so let's continue. Okay, yes, let's go. So to make this time, we'll take the square root of both sides, right? So I'll cancel this. We'll be left with what? V is equals to what? The square root of what? GME over what? Arrow, right? Yes. So this is the formula to calculate for orbital velocity when the satellite is at the surface of the Earth. Okay, yes. Now don't forget that G times ME is what? GRE square, right? Yes. So in the place of GME, we put what? We put we'll put GROE square, right? So in place of this, we'll put what? This. Okay, so now be what? G, okay, then all over what? Arrow, right? Yes, these two, they are the same. So we'll cancel one. We'll be left with what? One arrow E, right? Yes. So therefore, V cancel the V will now be what? Equals to what? Root G arrow E. Okay, so this is another formula. Okay, so this is the formula. These two formula. Yeah, we can use these two formulas to calculate for orbital velocity when the object is at the surface of the Earth. When the satellite is at the surface of the Earth. Okay, you can either use this or this. You can use anyone, and you will arrive at the same answer. Okay, yes. If for example they gave me the question coming out from this place, now how will you know that in the there was specified in the question? How will you know if you are going to use these two formula or we are going to use the other one? Now they will specify in the question. In the question they can say this the satellite is at an altitude away from the Earth. So in that sense, if that's the for the orbital velocity, you are going to use that previous one, that previous formula that I derived for you guys. Now, when they ask that the satellite is at the surface of the Earth, you can either use this or this to calculate for what their orbital velocity. Okay, so don't stress yourself. You use this. G is 9.8 or 10. They multiply by the radius of the Earth. That's why I told you guys to take note of radius of the Earth. Radius of the Earth is what? 6.4 times 10 to the power 6 meter. If you just do it, then take square root, you have your answer. You can still use this. G is 6.67 times 10 to the power minus 11. The mass of the Earth is what? Is approximately 6 times 10 to the power 24. Then you know the radius of the Earth. So yes, you can use any of this formula to calculate for what? To calculate for orbital velocity. Yes. Remember, it depends when the satellite is at an altitude away from the Earth or when the satellite is at the surface of the Earth. Okay, yes. So that is just it. Now there's what we call escape velocity. Now what is escape velocity? Escape velocity is that velocity with which an object used to escape the gravitation of the Earth. I don't even understand. That's known as escape velocity. For example, now let's say you launch a rocket. For example, the rocket usually the velocity with which the rocket is used to escape the Earth's gravitational pull. That velocity is known as what? It's known as escape velocity. Now, what is the formula for escape velocity? It's very easy. Escape velocity is what? It's usually 2 times the orbital velocity. It's 2 of the orbital velocity. So it's very easy. Escape velocity is what? 2. You put 2 of what? Of the orbital velocity. Okay. So if orbital velocity is what? G arrow E. Escape velocity will be what? Will be 2G arrow E. I don't understand. Okay, escape velocity will be what? 2GME. I'm coming. Divided by arrow E. Okay, so it's just 2 of the orbital. It's 2 of the orbital velocity. Okay, that is escape velocity for you. Okay, so that is just it. Okay, so take note of all the formulas I've placed in the board earlier. Take note of all this. Okay, you know the mass of the Earth, you know the sun, you know the mass of the sun, you know the radius of this, you know the radius of the Earth, you know the formula to calculate for orbital velocity when the satellite is at an altitude away from the Earth, or when it is at what? At the surface of the Earth. Okay, so yes, when it's at the surface of the Earth, okay, when it's at the surface of the Earth, the formula just now is what? Is G arrow E, right? Yes, or what? V is equals to GM all over yes, all over arrow, abi? All over arrow E. Yes, yes. So the square root, yes. So take note, there's no space for me to write all the formulas, okay? But so I'm just taking note of all the formulas, okay? Yes. All right. So there's still one part before we move to orbital period and tracking orbit before we move to the question and answer. Okay. There's still one thing I need to tell you guys. Earlier, I told you guys that satellites are not is a body that revolves around the Earth, right? Yes, it's a body that revolves around the Earth. Yes. So you guys that this body or this satellite usually they can usually move or revolve either in a circular orbit, or what in an ecliptic elliptical orbit. Okay, yes. Satellite they either move in a circular orbit. Most usually move in circular orbit, while some might move with um, um, in an elliptical orbit. Okay, yes. Now, when a satellite is usually moving in a circular orbit, this is a circular orbit. Let me clean here. Okay, let me clean here. Please take note of all this formula. Okay. So now this is let's say this is the Earth. Now this is satellite. Now this is circular orbit. Okay. Oh my God. Circular. You suppose know. Okay. So circular. You should know the comments. You should know that circular orbit from the word circular. Circular orbit is just circular in shape. Okay. Oh my God. Okay. Anyways, this is circular orbit. Circular in shape. Okay, so this is circular orbit. Now what about this circular orbit? Now what about elliptical orbit? Elliptical orbit will be something like this. Okay, this is the Earth. Elliptical orbit will be something like this. Okay. Yes, so this is satellite. Okay, so elliptical orbit something like this. This is circular orbit. This is what elliptical orbit. Okay. Yes. Now, when satellites when they revolve in a circular orbit, they usually revolve with what? With a constant. With please, this part is very important. With a constant orbital velocity. We all know the formula for orbital velocity, right? Yes. Now, the when satellites revolve in circular orbits, they usually move with what? With a constant. Very important is an exam-based question. With a constant orbital what? With a constant orbital velocity. Okay. Yes. Now, but when a satellite move in an elliptical orbit, the the orbital velocity varies. Orbital velocity varies. Exam-based question. Okay. Yes. When a satellite move in circular orbit, it moves a constant it moves the constant velocity because what? All the parts they are what? All the parts from the Earth, all the distance away from the Earth, they are all the same in all parts. Yes. Remember, I'm coming. Orbital velocity is equals to we all know when the satellite is far away from the Earth. Okay, so this is orbital velocity, right? Yes. Now, okay, yes. This is distance from what? Okay, this is orbital velocity, right? This is orbital velocity. Now, when a satellite is moving in a circular orbit, the distance between I'm coming. Let's say this is the Earth, for example. Okay, so this is the so this is the radius of the Earth, then this is the altitude, then distance from here to here will be r, right? Now, if the satellite is moving in circular orbit, the velocity is constant because why? The distance from the Earth, from center of the Earth to the satellite is usually the same at all points. I understand. So at all points, the satellite is moving with the same orbital velocity. The velocity does not change. Yes, but in an elliptical orbit, the orbital velocity varies because why? All the parts they are not what? They are not the distance between the Earth and the satellite is not the same at all the points. Now, please take note the parts of the satellite closer to the Earth is known as what? Is known as perigee. Perigee. Okay, yes. This part is known as perigee. While the part of the satellite away from the Earth that is farther from the Earth. Let's say the satellite was orbiting, then gets to this part. Now, you find that this point where the satellite is farther away from the Earth. This part is known as what? Is known as apogee. Okay, very important. Okay, apogee. The part away from the Earth is apogee. While the part closer to the Earth is known as perigee. Okay, yes. Now, if you look at it, in perigee distance arrow. Let's say for example distance between them. Yeah, for example, let's say it's 5. What about in apogee? The distance between them will be very large, right? So let's say 15. I you understand. For example, now let's say 15, for example. Found that distance from here to here is very in the apogee. Apogee, distance between the Earth and the satellite is usually very large. Then while in perigee, distance between the Earth and the satellite is okay, it's kind of close. It's not that large. Okay, yeah, the satellite is closer to the Earth at the perigee and farther away from the Earth at the apogee. Okay, now this velocity, right? Velocity is equals to, now if you look at the velocity is inversely proportional to what? To to the distance, right? To the distance. If you look at the formula, now velocity is inversely proportional to what? To the distance between the Earth and what, the satellite, right? Yes. So let's tell you that the higher the radius, the lower the velocity. Okay, the higher the velocity, the lower what, the radius. Okay, so let's tell you that the part where the radius is very high, which is apogee, the part where the radius is very high, which is apogee, the velocity is usually low. Orbital velocity is usually low. Now the part where the radius is very, where the distance between the Earth and the satellite is very small, the velocity will, the orbital velocity will be very high. So let's say, so this is why you find that orbital velocity varies in elliptical orbit. Okay, because in elliptical orbit, the distance between the sun and between the Earth and the satellite varies. Yeah, distance between them is, the distance is not constant. Unlike in circular orbit where everywhere you go, this distance is the same between the satellite and the Earth, right? Or in apogee, but in ecliptical orbit, the distance between the Earth and the satellite varies, okay, at different points, okay. The point which it is farther away from the Earth is known as apogee. The part which is closer to the Earth is known as perigee. So please take note, at perigee, the orbital velocity is very high. I never understand because why? Because this is the radius between them. The lower, according to this, the smaller the radius, the higher the speed. Yes. The larger the radius, the lower the speed because they're inversely proportional. Okay. So at perigee, the radius between the distance between the Earth and the satellite is small, and the velocity is very large. It's very high, right? So let's say this. Let me show you. Now let's say this is elliptical orbit. This is the Earth now. Let's this is satellite. Okay. Now let's say it's moving in elliptical orbit. Okay. Now when it gets to this place, it will just move like this zone. I understand. So the velocity here is very, unlike when it gets to here to be okay. It's kind of slow. Then I understand. So the velocity, orbital velocity is very high at perigee and low at where? At the apogee. Okay, because in apogee, distance between the Earth and the satellite is large. In perigee, distance between the Earth and the satellite is small. So orbital velocity varies in elliptical orbit and it's constant in circular orbit. You know the formula, I've shown you guys the formula for orbital velocity, right? Yes, now let's move to the last two parts, which is please take note of all the formulas I'll be giving you guys and all. Last part, which is orbital period and parking orbit. Okay, now orbital period. Now let's say what is orbital period? Now let's say this is the Earth, for example. Now orbital period is the time it takes the satellite to revolve to make one complete revolution around the Earth. That is known as orbital period. Now what is formula for orbital period? Now let me show you guys how to derive it. Okay. Now you all know that satellite is moving around the Earth in circular paths. That is which is provided by the centripetal force, centripetal force. So GFC, right? Yes, gravitational force provides the centripetal force that keeps satellite to keep on moving circular paths around the Earth, right? Yes. So what is G? What is FG? Is what? GME, then all over what? Arrow square, right? Yes. Okay. Then is equals to what? Centripetal force is what? MV square over what? Arrow. So this is the mass. This is the mass of the object of the satellite. And so then we want to get orbital period. So left we go GNE divided by arrow square is equals to V square over arrow, right? Yes. Now what is V square? Now what is V? V, we all know that V is what W arrow, right? From circular motion, V is what W arrow. Now let's continue W. But W is what? Equal to 2 pi over T. You understand? W, which is angular velocity, is equals to 2 pi over T. So the place of W, I put what? 2 pi over T here. 2 pi over T. Then don't forget about that, the radius, right? So in the place of V, I'll put what um 2 pi r over t in this place. Okay, so let's continue. So V is what? V is what? 2 pi um, R then over T. Then, okay, yes. Then, yeah, okay. So let me also make V stand alone first. Okay, so if you cross multiply, well, we arrive with V square, R square is equals to GNE times R. Then, yeah, yes. Then if you want to make V square stand alone by dividing both sides by R square, so on cancel, we arrive with something like this, right? We arrive with something like this. Now remember, I told you guys V is what? V is equals to what? 2 pi R over T, right? I've explained it just now. So in place of V, we put what? We put, remember V takes square, right? So we put 2 pi R over T, so the square of everything, right? So the square of everything will be what? Will be 4 pi square r square, right? R square over what? T square, right? Yes, the square of everything. Remember, it was something like this before. 2 pi r then over t all square. So if you take the square of everything, these two turn to 4, right? This one will take square, this one will take square, this one will take square, right? So take the square of everything. Okay, so I'm coming. Taking the square of everything, I arrive at what? 4 pi square r square divided by what? T square, right? Yes. Now, look at this side. This arrow will cancel this arrow. We will left with what? One arrow, right? Yes, we left with one arrow. So let's cross multiply. To cross multiply, T square will multiply G and E, right? Then this one will multiply what? Now be 4 pi square. Now arrow square times arrow give us arrow cube, right? Yes. Now let's go to this side. Okay. So now we are looking for orbital period, not to make T stand alone. We divide both sides by what? GNE, right? We divide both sides by GNE. So this one will cancel. We left with what? T square is equals to what? Is equals to 4 pi square r cube all over what? All over GNE, right? Yes. Now we are looking for T, not T square. So take the square root of both sides, right? We take the square root of both sides. This one cancel this. We arrive with what? T is equals to what? Now the square root of what? 4 pi square r cube all over what? GNE. Now the square root of 4 will give us what? Will give us square root of 4 will give us 2. This square root will cancel this square. So we're left with what? Pi, right? Yes. So we're left with something like this. R cube over what? GNE. Okay. So yes, because why? This square will cancel square root of 4 will give us 2. Now this square will cancel the square of pi. We're left with pi. Then we'll now be left with something like this. Okay, so everything. So orbital velocity. Orbital period will now be what? T is equals to what? 2 pi then r cube over what? GNE. So this is formula for what? This is formula for orbital period. Okay. Now don't forget, I told you guys that. Remember, don't forget the satellite that is moving. Okay, this is the Earth that is revolving around the Earth. Usually, what? Now, when the satellite is at an altitude above the Earth, now this arrow. Remember, arrow is what? Arrow is what? Arrow E plus altitude, right? Yes, radius of the Earth plus altitude. So in the place of arrow cube, I put what? I put what? Arrow E. I'm coming. I put arrow E plus height, then all cube, right? Yes, all cube. That is when the satellite is at an altitude away from the Earth's surface. So when the satellite is at an altitude away from the Earth's surface, the orbital period is 2 pi root arrow E plus h all cube, right? Then divided by what? Divided by GME. Now don't forget that GME is something as well. So I told you guys earlier that GME is equals to what? GRE square, right? So in the place of GME, I'll put what? GRE square here. So if I put it, now be what? GRE square. Okay, so this is the formula to calculate. Like there are different formula. Okay, so you can use any of them, you get your answer. You can use this to You can look for orbital period. You can also use this where we have GME. We can use this. So yes, so this formula for what? Orbital period. Okay, this one or either this. Okay, so this is the altitude of the satellite. The one is the radius of the Earth, right? Yes. So that is just it. Don't forget that this one is the radius of the Earth too. Okay, yes. So that is just it. So this formula for orbital period, they are the same thing. You can use any of them, you get your answer. Now move to the last part, which is parking orbit. Now we move to the last part, which is parking orbit. Parking orbit. Parking orbit is also called synchronous orbit, okay, or stationary orbit, okay. Yeah. Now parking orbit or stationary orbit. Now what does it mean? Now let's say this is satellite. Let's say this is the Earth. Okay, I'm coming. Yes, let's say this is the Earth. This satellite. The satellite is revolving around the Earth. Now, in parking orbit, the satellite usually appears stationary, but the satellite is actually moving. Just that the satellite is revolving at the same period as the Earth. I don't know if you understand. The satellite, the time it takes the satellite to revolve around the Earth now, this speed is the same as the time it takes the Earth to complete its rotation around its axis. I don't know if you understand. So in parking orbit, now what is the time? What time it takes the Earth to complete its axis? Rotation around its axis what? It's 24 hours, right? Yes, 24 hours. So in parking orbit, the satellite is usually moving at the same period as the Earth when the Earth is rotating around its axis. So the satellite is also revolving around the Earth at this same period, which is what 24 hours. Okay, so that is why the satellite usually appears stationary when you look at it. To appear stationary because the Earth and the satellite is usually moving at the same period. I don't understand. So to look at it, the satellite is not moving, whereas the satellite is actually moving. Okay, so that is just parking orbit. The important thing to take note of other parking orbit is that the orbital period of the satellite is what 24 hours. Okay, so 24 hours. You can convert it to seconds or minutes. Okay, so yes, so this is all you need to know about. This is all you need to know about gravitation. Yeah, relating to PHY101, which is another level course. Okay, so now let's move to the next part, which is question and answer before we call it a day in gravitation. Okay.